Hello and welcome to the second part of this introduction to spectrophotometry on waves. This will be part 2. So I want to begin by just recapping a little bit on the last thing that we covered last time, which was this idea of transmission of radiation. Now, this is an important concept because today we'll be talking about the different processes that can happen to waves and how they can be utilized in some of our measurements, and looking a little bit at some of those processes involving waves and how they precisely can be measured and what their typical spectra may look like. But the transmission of radiation is key because oftentimes we're considering a medium, which may or may not be our sample, through which our radiation is propagating. So we often have, for example, an incident beam, and then it has some degree to the normal being this vertical line coming out from the interface. So this normal will be 90 degrees typically to the interface. So if this is the interface here, this blue line, then this would be the normal. So that has some angle, and that angle may or may not change as it passes through the medium. More often than not, it does change. And this can change things like the wavelength, but it usually does not change things like the velocity. So the other thing is that this angle will be recovered upon exiting the medium. So the change in angle or otherwise, or the speed or the wavelength is only inside of that medium. And as we go back outside again, what will happen is that we will recover the original characteristics. So say we're in air, then the medium, and then air again, both sides of the medium will be the same in terms of the radiation propagation. So the rate radiation propagates through a transparent substance is less than its velocity in a vacuum and depends on the kinds and concentrations. Radiation must interact in some way with matter in its path, and frequency change is not observed. However, the interaction cannot involve a permanent energy transfer. Refractive index of a medium is one measure of its interaction with radiation and is defined as so, where Ni is the refractive index at a specific frequency. So remember, these refractive indices are only particular for a particular frequency. C is going to be its velocity in a vacuum. And since we're usually dealing with light, it's going to be the speed of light. And V is going to be its velocity. Vi is the velocity of the radiation in that medium. So here are the 5 kind of things that typically happen with our electromagnetic radiation, the physical interactions that we can do. And these are things that we can make use of in order to tune our measurements. So these are the sort of processes which are happening inside of our spectrometers in order to produce the measurement that we interpret and utilize in our everyday analytical instrumental chemistry lives. These are the processes which will eventually become figures and data in our reports, through which we can then certify our products or otherwise. So physical interactions, so these are not dependent on the characteristic of electromagnetic radiation. And they can take the following types, which the first one is going to be reflection of radiation. The second is going to be refraction of the radiation. And so this will be similar to what happens whenever we transmit a sample. Then we'll have diffraction of radiation, scattering of radiation, and polarization of radiation. We will spend some time looking at each one of these in turn. Then the last one here is chemical interactions, which are dependent on the characteristics of electromagnetic radiation. So refraction of the wave. So here we have two mediums, medium 1 and medium 2. This medium 1 could be air and medium 2 could be glass. And this is a normal, which I talked about, which is at 90 degrees to the interface. The interface here, this black line, and then the dashed line is the normal, which is at 90 degrees to that interface. So refraction is the change in direction of propagation of a wave due to a change in its transmission medium. Refraction of light in passing from less dense to a more dense medium and bending, this is bending towards the normal. So whenever we go from less dense to more dense, what we have is a bend towards the normal. So you can see here that initially this is an angle of about, say, 45 degrees, and then it becomes an angle of about 30 degrees as it passes through the medium. So this is the angle between the vector of the propagation of the electromagnetic radiation and the normal. So less dense media to more dense means that we will have a bend towards the normal. And conversely, if we go from more dense to less dense, we will have a bend away from the normal. And so we can then, the extent of refraction is given by Snell's equation, which is seen here, where sine theta 1, where theta 1 is this angle in medium 1, over sine of theta 2, which is the angle in medium number 2, between the normal and the vector, is going to be equal to the refractive index of medium 2 over the refractive index of medium 1, which is going to be equal to the velocity through medium 2 over the velocity in medium 1. So this is Snell's equation, which gives the extent of refraction as a ratio between the speeds or the refractive indices or the angles between the normal and the vector. Reflection of radiation, which should hopefully be quite familiar to you. This is what happens whenever we look in a mirror, for example, or any reflective surface. So what's happening here is the light is being reflected off the surface and back away from that, and the angle at which it reflects, is going to be dependent on the angle that it is incident. So reflection occurs when radiation crosses an interface between media with different refractive indices. Reflection increases when difference between refractive indices is large. And for radiation that enters an interface at right angles, it is reflected, the reflected fraction is given by this, where the intensity of the reflected light is going to be, it's going to be a ratio of reflected intensity over incident intensity, which is going to be dependent on the difference in refractive indices between the two surfaces. So this will be surface number 2, so that will be where the reflection is taking place, and N1 is the other media. So then we have that over the sum of the two media, and so this is how we would determine the reflected fraction of light from two different media. So this can have, like, I mean, the classic example that we have is of course the mirror, but we can have a certain degree of reflection from any surface. It just really depends on how the refractive indices differ. So this was reflection. So you can see here that usually there's an incident angle, this theta I, and there's a reflected angle, this theta R. And so there is the P, which is the incoming, and there's the Q, which is the outgoing. Laws of reflection then. So we have two different types of reflection. We have incident, if we have an incident light on a certain point, we have two types of reflection. We have diffuse reflection, which occurs in all directions. And we have specular reflection, which should hopefully be the predominant form of our reflection, if reflection is what we're aiming for. So the laws of reflection: incident ray, the reflected ray, and the normal to the reflection surface at the point of incidence lie in the same plane. So they're all in the same plane. And the reflected ray and the incident ray are on opposite sides of the normal. So the normal is the vertical line that goes up from here. And we have here that the incident light is here, and then the normal is at the point at which the light is incident on the reflective surface. And then we have from that this specular reflection. So specular reflection of light from a smooth surface is a mirror-like reflection. So you can see here in this valley, we have these mountains and cliffs, and they're being reflected almost perfectly in this very still lake. So reflections on still water are an example of specular reflection. There we go. A diffuse reflection then is reflection of light from a rough surface, retaining the energy but losing the image. So here we have incident light onto a rough stone surface or some sort of lattice. So the light is incident here, but it is going to be reflected in both primary and secondary forms. So you can see here we have incident light, and then it is reflected here in the dark blue as primary reflection. But then these primary reflections end up hitting a surface and forming secondary reflections. So you can see this actually if you have, like, for example, a very shiny metal object like a kettle or something like that. You can see that there are going to be multiple different spots, which are, if you shine a light on it or light is coming from one direction, you may see multiple different like bright spots, like white spots if it's a silver kettle. And those are the secondary reflections. The primary one is the brightest one, and then there will be some others either side of it, and those are typically the secondary reflections. So diffraction of radiation. So what can happen here is that if we have, for example, planar waves like these, then if we pass them through a slit, what can happen is that the waves can be bent. As you can see here, they enter as plane waves here, and then eventually they become more spherical in shape. Although because the gap is very large, what ends up happening is it's not terribly curved. But if we close this aperture more, what happens is that we end up getting these spherical waves like so. And so you can see this if you go to like a small port or a seaside town or something like that, and they have like a place where the boats stay inside of the sheltered dock. Usually there's like a small opening there. If it's particularly rough seas, then you can often see like the waves that as they come towards that start to become, instead of moving in a straight direction, they become spherical. Then that's a acoustic wave actually, but these laws typically apply to both in cases of, for example, diffraction. Scattering of radiation. So this is what we make use. We make use of this whenever we want to know particle size. So, for example, if we have a particular sample, maybe it's a dispersion of small droplets in water or something like that. What we can have is the interaction with small particles causing scattering of the radiation. And the scattering it can be related to the diameter of the object by scanning over multiple different wavelengths and seeing how the light scatters as a function of wavelength. We can determine the diameter of the average particle. So scattering of radiation. So interaction with small particles scatters the radiation. Scattering by molecules with sizes smaller than radiation wavelength is called Rayleigh scattering. Rayleigh scattering causes the blue color of sky, and it's caused by the greater scattering of the shorter wavelengths of the visible spectrum. And the scattering by large molecules can be different in different directions and is called Mie scattering, used to determine the size and shape of colloids. So you can see here a couple of examples of scattering from biological samples, and we have incoming beams here. And since the wavelength here is going to be approximately equal to the diameter, what ends up happening is that we get different amounts of scattering light. We get forward scattered beam, which is all in phase, and then we get sideways scattered beam, which is going to be the out of phase one, which happens. So we can then also see what happens whenever the wavelength is much larger than the diameter, and we end up not really getting a lot of usable information here. But we can still make use of this in our analytical measurements. Radiation. So, okay. So in the first part, we learned that about waves, and we learned about some of their properties, like their amplitudes. We talked about frequencies. We talked about wavelengths and things like that. I also briefly mentioned that as waves propagate, we often look at them as sine waves in 2 dimensions. So they just look like this curve. But what's actually happening is that the light is propagating in all directions. So monochromatic radiation has an equal distribution of planes centered on the beam path. So the beam path is what this line is. But around this line, if we were to look at it end on, so as the beam was coming towards us, it would look more like this, where the light is being expressed in each direction. So the light vector is actually all around the beam path. It changes in intensity, obviously, and the amplitude changes as we go along. But ultimately, the light is going to be expressed in all directions. It looks like here, like there's only a certain number of lines, but actually, that's just to represent that it's totally spherical. Like the light is totally expressed in all directions, 360 degrees. But what we can do is we can polarize the light. So what happens is that we create some sort of material which cuts out the beam except in a certain direction, kind of like a slit or something, which can force the light into a particular shape. And this is then called polarized light. And typically we want to remove all but one of these planes of light. And so what we do is we create plane polarized light. Usually we create horizontally and vertically polarized light. So this would be vertically polarized light because it is vertical with respect to the normal. There are different types of polarizers. One of the simplest ones, I guess, is a wire grid polarizer, which is just, you can see here, we have a light source. A fine wire grid polarizer, and it absorbs all of the light in all of the directions except the one which is perpendicular to the lines. And then that produces a plane polarized light. And so when we get to our detector, we only detect light that is vertically polarized. So the wire grid polarizer is a regular array of fine parallel metallic wires placed in a plane perpendicular to the incident beam. Electromagnetic waves, which have a component of their electric fields aligned parallel to the wires, induce the movement of electrons along the length of the wires. And since the electrons are free to move in this direction, the polarizer behaves in a similar manner to the surface of a metal when reflecting light, and the wave is reflected backwards along the incident beam minus a small amount of energy lost to the Joule heating of the wire. So what's happening here is any of the waves which are in any way not perpendicular to the direction of these wires will be partially absorbed and reflected by the wires, and some of that energy will be transferred to the electrons, which will heat up the polarizer a little bit, and the rest will be reflected backwards. And that's ultimately how it works, because if any, like even if it's like almost perpendicular, even a slight deviation from that means that it can actually interact with these wires, and the only one that cannot is the one which is exactly perpendicular. And so it does not get reflected, it does not interact with the wire grid polarizer, and it continues on through, and we have our plane polarized light. So we have some other types of polarizers. We have a nickel prism, which is a birefringent polarizer. So what it basically does is it splits the light into two different beams. At the same time, it polarizes them into both vertically polarized and horizontally polarized light. We have two rays. We have the ordinary ray and we have the extraordinary ray. And so this birefringent polarizer consists of a crystal of calcite, which has been split and rejoined with Canada balsam. So it's one crystal which has been split in two, and then there's been some Canada balsam put in the middle. And then this Canada balsam creates like an interface change, which is where the two beams are split. One is going to be reflected and the other one is going to pass through, depending on its polarization. And you can see here that as it comes incident in the material, because of its different polarizations and its different interactions with the crystal, it will start to get separated, but it's really whenever it hits this interface between the two parts of the crystal that we get a little bit of a reflection, and we end up creating the two different rays. And then this other one here is a Wollaston prism, and it's another birefringent polarizer. It consists of two triangular calcite prisms with orthogonal crystal axes that are cemented together. At the internal interface, which is here, an unpolarized beam splits into two linearly polarized rays, which leave the prism at a divergence angle of between 15 and 45 degrees. So you can see here that they hit this interface here, and then they're split into the vertically and horizontally polarized lights, and they're separated by this by 15 to 45 degrees. And so that's sufficient to be able to then redirect the light in some way. So there's three main polarizers that we make use of: the wire grid, the nickel, and the Wollaston prism. All of these, depending on your instrument, may or may not exist inside of your spectrometers, and they're usually very fundamental to the operation of those. We don't normally come in contact with them whenever they're in our instruments, unless we need to do some work or unless we have built an in-house instrument. But they are there and they're important aspects of our instruments. So here's a bit of a summary of some of the interactions of light and matter. So if we have a particular interaction, what radiation we're measuring and what spectroscopic method that pertains to. So for example, absorption and transmission. we have incident light, we have transmitted light. We will be looking at things like atomic absorption, and we will be looking at things like molecular absorption. If we have, for example, emission, then we'll be looking at the intensity of emitted light. This will be atomic emission, molecular emission, and chemiluminescence. We'll be going on here and we will be talking about things, both emission and absorption measurements. Absorption of radiation. So this is one of the key processes which are going to be kind of based on that idea of transmission that we had earlier, in that through the absorption of radiation, we can make a lot of spectroscopic measurements. This is going to be fundamental in emission spectroscopy and in absorption spectroscopy. In absorption spectroscopy, we measure it directly, but in emission spectroscopy, we measure the emission after an absorption event has happened. So the absorption of radiation occurs only if there is an interaction between the electromagnetic radiation and the material. So this means that sometimes certain wavelengths of electromagnetic radiation can just pass through a material without anything happening. Like, the absorption has to be related to some sort of internal process in our analyte, in our sample. So for example, in the case of UV-vis spectroscopy, typically we're looking at electronic transitions. So from electronic ground states up to certain excited states, that would correspond to an absorption. If the wavelength doesn't correspond to one of those excitations, then it just doesn't absorb it, it passes straight through. And so that would give us our peaks and lack of peaks. And the energy of the electromagnetic radiation must exactly correspond to the energy of the transition in the molecule. So yeah, that's what we were talking about. So the incident intensity then passes through the sample, then the beam comes out, and where I is after absorption happens. So the final intensity must be less than the initial intensity, but the absorption depends on the population and path length. So depends on concentration, and it depends how long it has had to interact with the sample. So this is kind of related with those energy states inside of molecules. So you may have come across this in physical chemistry classes. So inside of atoms, ions, and molecules, we have electronic states. And there can be transitions between these states, typically from lower to higher energies, if there has been an absorption. So when a material changes its state, it absorbs an amount of energy exactly equal to the energy difference between the states. So it can be described by this equation, where the energy at the excited state minus the energy of the original state is equal to h nu, which is equal to hc over lambda. And this is, of course, our Planck's equation. And this on this side, it's now the difference in energy states. So for example, we have two energy states here. We have E0, the ground state, and E1, which is some higher energy state. Then we can have some absorption of energy, electromagnetic radiation, which will cause an excitation from this ground state up to the excited state. Now, the various energy states are called electronic states, and the lowest energy state of an atom or molecule is called the ground state. Higher energy states are termed excited states. Most species are in the ground state at room temperature. So absorption of radiation. When radiation passes through a sample, certain frequencies may be selectively removed by absorption, a process in which electromagnetic energy is transferred to the atoms, ions, or molecules. Absorption promotes these particles from ground states to one or more higher energy states. It may not be the first higher energy state, it could be the second, or it could be the third. It just depends on whether or not that wavelength corresponds to that transition and if there is sufficient energy. The energy of the exciting photon must exactly match the energy difference between the ground state and one of the excited states of the absorbing species. So since these energy differences are unique for each species, a study of the frequencies of absorbed radiation provides a means of characterizing the constituents of sample matter. So here we have sort of a schematic of what's happening here. So we have incident radiation, which has got an intensity of P0, passes through the sample, some of it is absorbed, and then what is transmitted is given P and is going to be less intense, as indicated by the difference in the arrow sizes. And the energy that has been absorbed by the sample corresponds to these energy transitions. So it could be 0 to 1 or 0 to 2. And so energy 1, E1, is going to be this 0 to 1 transition, and E2 is going to be the 0 to 2 transition. And so that would correspond to two different peaks. We have here lambda 2, which is the second level, and lambda 1, which is the first level. Lambda 1 is more intense because it is going to be easier to achieve because it is a lower energy requirement. So, and also the population in this state is more easily excited to the first state. So radiation of incident radiant power, P0, can be absorbed by the analyte, resulting in a transmitted beam of lower radiant power, P. For absorption to occur, the energy of the incident beam must correspond to one of the energy differences in an atom or a molecule. So this gives rise to an absorption spectrum, which is a bit idealized here, but you get the idea. Absorption types then, so atomic absorption is the passage of polychromatic ultraviolet or visible radiation through a medium that consists of monoatomic particles, results from the absorption of a few well-defined frequencies, and such spectra are very simple due to the small number of possible energy states for the absorbing particles. Molecular absorption then is absorption spectra for polyatomic molecules, and they are considerably more complex than atomic spectra because the number of energy states of molecules is generally enormous when compared with the number of energy states for isolated atoms. The energy E of a molecule is made up of three components. It's made up of the electrical energy, which is the electronic state. So those are the largest differences. The vibrational energy, so that's the vibrations of particular bonds, and rotational energy, which is the rotations of different atoms within those bonds. So they go in that order. So electronic energy is the largest, then vibrational, and then rotational. So in absorption spectra, we have some on the right-hand side here. We have sodium vapor, which you can see is atomic and has very well-defined peaks here and here. But then for molecules, it's much more complex. So if we have benzene in the gas state where we have individual molecules, what we end up seeing are some sharp peaks, but it's a very complicated spectrum compared to the sodium. In the case of benzene and hexane, we can see the effects of the solvent. So it creates this smoother picture, which is less well defined because of the interactions of the benzene with hexane. And then biphenyl and hexane, you can see, is just a continuum. There's no real structure to this. So absorption spectra can have different forms. Sharp peaks or smooth are common. Spectra are affected by complexity of the sample, the physical state, the environment of the absorbing species, and the biggest difference is between atomic and molecular spectra. And these two at the bottom show us that the matrix of the sample can have a big effect. But we already knew that from our introduction module, where we talked about how the matrix can have an effect on things like our calibration curves. So radiation emission then, so this is the other side of the absorption coin. So in this case, we're no longer looking specifically at the light which is absorbed, rather we are looking at what happens after the light that is absorbed, and then those excited state molecules or atoms return to the ground state. So emission of radiation, so electromagnetic radiation is produced when excited particles such as atoms, ions, or molecules relax to lower energy levels by giving up their excess energy as photons. And the radiation from an excited source is characterized by means of sample. Absorbs some energy, goes to X dot, which is an excited state. And then this X dot then relaxes back down to the ground state as X plus this release of energy, which is given here as Planck's constant. But remember that E is equal to h nu. So this is the same as that because this energy is released as light. So the excitation can be done by bombardment with electrons, electron current AC spark, heat of a flame, an arc, or a furnace, like we can produce UV, Vis, or IR radiation from this, or the beam of electromagnetic radiation may be coming from a lamp as well, a lamp source. Photoluminescence then, so these methods include things like fluorescence and phosphorescence. So photoluminescence results from absorption of electromagnetic radiation and then dissipation of the energy emission through radiation. Then absorption can cause excitation of the analyte, and once excited, the excess energy can be lost by emission of a photon. And emission occurs over all angles and wavelengths emitted correspond to energy differences between the levels. So here we have incident radiation, which has got a power of 0. This then passes through the sample. And then we have the transmitted radiation, but we don't place our detector here. Instead, we usually place it at 90 degrees to the sample, and then we collect the luminescence, the PL, the photoluminescence. And so you can see here that there are a number of peaks which correspond to different things. So we have here the transitions, for example, excitations from the ground state up to the first excited state, or excitations from the ground state up to the second excited state. We could even have further excitations from the first excited state up to the second excited state, but we're not encountering that right now. But we have 3 peaks here, whereas before for the absorption, we only had 2. So this third peak is a much smaller peak, and it represents the relaxation from the second ground state down to the first ground state. So typically we have second down to 0, which is this one, which got a smaller population or a smaller intensity, which corresponds to a smaller population because there are fewer molecules in that. And then this lambda 1, which represents the 1 back down to 0 peak, it has the largest intensity because it has the largest population. And so the largest number of molecules will relax from that state. Emission spectra then, so there are 3 types of emission spectra. We have line spectra, we have band spectra, and we have continuum spectra. So the relaxation processes, the lifetime of an atom or molecule excited by absorption of radiation is brief because there are several relaxation processes that permit its return to the ground state. So non-radiative relaxation. So non-radiative relaxation involves the loss of energy in a series of small steps. The excitation energy being converted to kinetic energy by collision with other molecules. A minute increase in the temperature of the system results. So here we have an emission spectrum which shows a couple of different types here. We have band structures and we have line structures. We don't have really continuum except this broad increase. So the lines are, as you would expect, these very sharp peaks. They are peaks, but they're typically referred to as lines because generally they're very narrow and they really just have a very sharp point. So these are all line spectra. But here you can see band spectra where we have like a bunch of different peaks which are clustered together, and there are groups of lines that overlap and they're not fully resolved, but we can usually sort of notice the peak positions. And then continuum, this is an increase in background spectrum like this. So you can see here that changing wavelengths, we have generally an increase in the intensity or the background spectrum, and that is a continuum part of the emission spectra. So atomic versus molecular emission spectra. So atomic spectra is equal to single lines, and molecular spectra typically looks like a band spectrum. And so you can see here the differences. So here we have atomic spectra, and here we have a molecular spectra on the right-hand side. So what's happening is we have single excitations up to either the first or the second or third or fourth different energy states. And then we have single emission lines, which are single lines. So these are the atomic emission spectra. But in molecular emissions, we have excitation up to different excited states, but then our emission is back down to multiple different vibrational states. And because these lines here are vibrational lines, and they result from the fact that molecules have bonds between the atoms. And so that means that the relaxation doesn't just happen back down to the electronic ground state as it does in an atom, because atoms don't have vibrations because they don't have bonds. We end up with a more complex spectra caused by these different vibrational energy states. Fluorescence and phosphorescence relaxation. So fluorescence and phosphorescence are analytically important emission processes in which atoms or molecules are excited by absorption of a beam of electromagnetic radiation, and the radiant emission then occurs as the excited species returns to the ground state. Fluorescence, which is a very fast process, occurs more rapidly than phosphorescence. To the excitation beam, and so you can see here general schematic of what's happening there. So we have incident beam, and it passes through the sample. And then we have the exiting beam here, which is after the sample has absorbed some light. We don't actually measure this. Instead, we place our detector at 90 degrees to the sample, and we detect our fluorescence and phosphorescence. Now, because the intensity of the fluoresced light or the emission spectrum is much lower, we have to kind of protect the detector from any potential leakage of the excitation beam. And so you have to design your spectrometer in a certain way to try and block out as much of this light from the incident beam as possible. So that's why it's at 90 degrees, because that's typically where the smallest amount of reflected or incident light will be. So here's a schematic of the luminescence again, just that we saw earlier, but now in a larger picture. So we have incident radiation, we have our sample, we have our transmitted radiation, which we don't want. Then we have our luminescence, which occurs in all directions. There's no real way to control this, but so long as we get some of it, we can still plot the peaks and we can determine the sort of intensity there. So we place it at 90 degrees, and then these peaks are going to correspond to these different processes which are occurring. This is for an atomic species. If it's for a molecular species, as we saw earlier, it's going to be much more complex. Fluorescence, resonance fluorescence describes the process in which the emitted radiation is identical in frequency to the radiation employed for excitation. And so resonance fluorescence is most commonly produced by atoms in the gaseous state that do not have vibrational energy states superimposed on electronic energy levels. So yeah, so basically we don't have the vibrational energy states, so any relaxation will have the same frequency as any excitations which are absorbed. Non-resonance fluorescence is brought about by irradiation of molecules in solution or in the gaseous state. So this is the idea that there is a difference in the wavelength of the light absorbed and emitted by the molecule. So there can still be resonance fluorescence in a molecular spectrum. That is possible. But there is also a complication factor because of the vibrational energy states. So as it relaxes back down to the vibrational energy state, the energy differences between those states are all different. And so since we know that energy has some correspondence to the wavelength, it means that the wavelengths can change. And so that's why we have non-resonance fluorescence. So excited state lifetimes. So the lifetimes of these excited vibrational states are only on the order of 10 to the minus 15 seconds, which is much smaller than the lifetimes of the excited electronic states. The vibrational relaxation typically occurs before electronic relaxation, and the energy of the emitted radiation is lower than that of the absorbed radiation by an amount equal to the vibrational excitation energy. So here we have the ground state, we have the excited state, and we have the ground state again. So we have an excitation which excites the electron in this Bohr model from this energy state to a higher energy state. So it goes to an excited state here. You can see it leaves behind a hole. And then this hole is then filled again as the electron eventually will relax down to the ground state very quickly. I mean, on like much faster than a millisecond. And then it emits the light. So phosphorescence occurs when an excited molecule relaxes to a metastable excited electronic state called the triplet state, which has an average lifetime of greater than about 10 to the minus 5 seconds. So here we can see some of the energy level diagrams involved with fluorescence. So IR gives pure vibrational spectra because energy of radiation is insufficient to cause electronic transition. So its existence is all purely within the vibrational states. It never gets to a higher electronic state. It doesn't have enough energy for that. A non-radiative relaxation involves the loss of energy in a series of small steps, the excitation energy being converted to kinetic energy with collision with other molecules. And so we see a small increase in system energy. And so the resonance fluorescence is going to be emitted. So the resonance and fluorescence is going to be emitted radiation is identical in frequency to the excited radiation. We found out about that earlier. So we can see over here on this diagram, which is very useful for us to see the different types of transitions within a molecule or within energy states. So we have here absorption of energy. So we have like how they correspond to different types of radiation. So IR radiation is typically very low in energy, and so it can only really excite within the vibrational energy levels of a particular ground state. So this electronic ground state is where the IR energy is going to stay. If we cannot provide enough energy to get to the first excited electronic ground state, but visible electromagnetic radiation can get there, UV can also get there, other high energies like X-ray can also get that. These small lines, these like kind of narrow lines, these are the vibrational energy levels. And so this is the absorption process where different wavelengths of light are being absorbed because they have different energies. Remember from our Planck's equation, we have E is equal to H nu, where nu can be replaced with C over the wavelength. So the wavelength corresponds to the energy of a particular transition. A non-radiative relaxation sees the relaxation within excited states, within vibrational states. We can see here that there are a great many different processes occurring at different energy states. And so even within the IR regime, there are a great many different transitions, which can cause a great many different and then fluorescence is going to be the relaxation from higher electronic ground states down to different vibrational levels, or the whole way back down to the electronic ground state. Typically what happens is that we have this non-radiative relaxation between the vibrational levels down to the lowest energy vibrational level of a particular excited ground or a particular excited electronic state. And then from that electronic excited state, we see the relaxation down to lower vibrational energy levels, lower electronic states. So typically you see this fluorescence happening from the vibrational ground state of a particular excited electronic state. The classes of spectrochemical methods. So we have emission type, we have luminescence type, we have scattering type, and we have absorption type. So we see here emission is related to atomic emission. Absorption, for example, is emitted to atomic and molecular absorption. And so there is a difference between emission, luminescence, and scattering and absorption. And it's the sense that these three are going to be proportional to the power of the radiation emitted by an analyte after excitation, and it is proportional to the concentration, whereas the absorption is going to be dependent on the energy of the beam. So emission, luminescence, and scattering methods, the power of the radiation emitted by an analyte after excitation is usually directly proportional to the analyte concentration. So these three, the first three, are going to be significantly different from absorption. So quantitative absorption methods require two power measurements, one before the sample and one after. So absorption methods, so quantitative absorption methods require two power measurements, one before a beam has passed through the medium that contains the analyte and the other after the sample. So these two terms are widely used in absorption spectroscopy and are related to the ratio of P0 and P, and they are transmittance and absorbance. And spectrophotometry is a method to measure how much a chemical substance absorbs light by measuring the intensity of light as a beam of light passes through the sample solution. The basic principle is that each compound absorbs or transmits light over a certain range of wavelengths. So transmittance is the transmittance T of the medium is the fraction of incident radiation transmitted by the medium. So T is going to be equal to the incident power, the final power over the incident power. So this will value from 0 to 1, 1 where the the sample is not absorbing any light, where P0 is the incident power of the beam and P is the power of the beam after absorbed by the sample. Transmittance is often expressed as a percentage, so percent transmittance, which is equal to the final power over the initial power times 100%, with again a value from 0 to 100%. And then absorbance is going to be is given letter A of a medium is defined by this equation, where A is equal to minus log to the base 10 of T, which is equal to minus the log 10 to the base 10 of the ratio between the final power and the initial power, which is equal to the log of the initial power over the final power, which is then equal to the log of 1 over T. So these are just log relationships, really. If you remember one of them, you can usually get to the others, because remember that T is going to be related to the ratio of the powers, like so. So again, this is kind of what it looks like in our instrument. We have some incident beam of light, we have some emitted beam of light after interaction with the sample, and we have some cuvette, which has got a path length B, and then we have the solution inside has some concentration C, and then we can create what's called the Beer Lambert Law, which we'll see on the next slide. So power is higher before the sample, and then power is lower after the sample, assuming that some absorption has occurred. So the Beer Lambert Law, for monochromatic radiation, absorbance is directly proportional to the path length B through the medium and the concentration C of the absorbing species. These relationships are given as A is equal to ABC, where A is the proportionality constant called the absorptivity, and the magnitude of A will clearly depend upon the units used for B and C. For solutions of an absorbing species, B is often given in terms of centimeters and C in grams per liter. So what's happening here is we have, for example, A is going to be specific to a particular analyte. So the absorptivity has the units of liters per gram per centimeter. When the concentration is expressed in mole per is given the spectral symbol epsilon. Thus, when B is in centimeters and C is in moles per liter, A is equal to epsilon BC, where epsilon has the units L per gram per centimeter. The above equations are an expression of the Beer Lambert Law, which serves as the basis for quantitative analyses by both atomic and molecular absorption methods. So here is a typical absorption spectrum setup or absorption instrument setup. So you would have some light source. In this case, it's a tungsten lamp, which produces monochromatic light. Then you would filter that, you would colliminate that. So you would create parallel beams of light. Then you would filter that out. So you would get rid of any particular wavelengths that you don't want. Then you would have a shutter to kind of cut the light on and off. So you can turn the light off. Then you might have a variable diaphragm to set 100% transmittance. So this kind of normalizes the beam to an extent. Then you would have two different spots for your sample. You would have a solvent cell, which would be your blank, and you would have the sample cell here. Some instruments split this beam of light so that you can measure both simultaneously. Others have like a little shuffle mechanism where you can pull a lever and it will move the two cuvettes into the beam and out of the beam. Then the light will pass through those, and then some of it will be absorbed, and then the photoelectric device will detect the light, and then it will convert that light as a response into an electrical response, which will then be transmitted through the circuit to give a readout in a digital meter. So here we have percentage transmission. So a photoelectric device is a transducer that converts non-electrical signal to electrical signal. Remember always through this process that in the electrical response and then convert that back into the measurement that we want. Okay, so that's the end of part 2 on waves. We've talked a lot about different processes involving waves and a little bit about some instrumental methods and processes. So let's do a comprehension check. So as always, I'll read out the question, then we'll pause for a moment to allow for you to try it yourself. You can pause, of course, the video for more time, and then we will go through it. So absorptivity of a sample what is the absorptivity of a sample if its absorbance is 1.2 atomic unit or arbitrary units when the path length is 1.0 centimeters and the concentration is 0.8 molar? Okay, so this is going to be a Beer Lambert question, so please pause for more time if you need it, or do this calculation. Okay, pause for more time if you need it. Want to go through the answer shortly? Answering now. Okay, so we're recalling that the Beer Lambert law is A is equal to epsilon BC, where epsilon is the molar absorptivity. So we rearrange the Beer Lambert equation so that it's in terms of the molar absorptivity epsilon, which is equal to A, the absorbance, over B, the path length, times C, the concentration, all of which were given in the question. We then fill in these values into the equation. So it's 1.2 over 1 centimeter times 0.8 molar, which will give us a value of 1.5 per mole per centimeter as our molar absorptivity. So that's how we would calculate the molar absorptivity of a particular sample given this information. So thank you for watching. Bye-bye.